So, in this lecture, this is lecture 3.2, and in this lecture we're dealing with the Bohr model of the atom and how the Bohr model of the atom reacts when you apply energy to it, and when those electrons, they get excited and then they move back down to what we call their ground state. So we're going to look at all those terms, but the Bohr model did a nice job of explaining that behavior when atoms were excited and when electrons changed positions. So the person who did a lot of work with that, his name was Niels Bohr. Niels Bohr, and he did a lot of work at this right around the turn of the century when all this stuff was coming out, and you had J.J. Thomson, you had Ernest Rutherford, you had all of these great chemists that were coming out with these new models of the atom, and it was really a lot of revolutionary work, and we'll talk about a few next time in lecture 3.3 that really kind of started to understand how complex an atom really is. It's not just as simple as J.J. Thomson and Rutherford thought it was. But Niels Bohr was one of the first people that did a lot of work with this, and he did not only a lot of work developing the structure of the atom, he also was a major factor in the events of that day. He lived most of his life in Denmark. However, when the German occupation started to infiltrate into Denmark, he was a Jew himself. He was of Jewish descent, and he kind of took his family in kind of a daring escape, it says in the book. It says he kind of escaped by boat over to nearby Sweden, and therefore he was then transferred kind of by a British Navy plane in an empty kind of, it says an empty kind of armament case, kind of like hidden in the plane. He made it to Great Britain, and he kind of lived out a lot of his life there. He was also a major factor in the Manhattan Project. He made his way all the way over to Los Alamos, New Mexico, and he was a major factor in the help to find or to figure out the how to make an atomic bomb. And then after that, he became a very, very big advocate against the use of nuclear weapons. So what I'm talking about is he kind of noticed with the help of a device called a spectrometer. A spectrometer. So what a spectrometer is we have a source of light here, and it enters the device, the spectrometer, through one optical end, and then it goes through and it hits a prism here in the center, and that prism splits that light up into readable wavelengths of light. So your eye is kind of right here, and you're looking at that wavelength of light. So around this edge here, I'll show you one in class, around this edge here it has different wavelengths of light, or different measurements of wavelength, and you can see what the wavelengths of light that are given off by an atom are. So what was happening? So Bohr tried to kind of understand what he was seeing when he saw these spectral lines. So basically his atom, or his model of the atom, said that electrons inhabit distinct energy levels. Okay, so and the energy levels were a certain distance apart from each other. So I have say I'll have an electron here. When that electron gets excited, sorry about that there. When that electron gets excited, it's going to move to an excited state. It's going to move to a next higher energy level. Okay, and atoms don't like to have empty inner energy levels. So another electron might jump down from that next energy level to take its place. Okay, and when that happens, energy is transferred. So energy has to come into the atom in the form of a wave. Energy kind of takes the form of a wave. So it excites that electron to get it to move out. Okay, so therefore the atom has to give off energy for an electron to move closer to the nucleus. So it gives off a certain wavelength of light there. So that happens first, and this happens second, and this is the light that we see, the spectral lines in the spectrophotometer over there. So what did that mean? Okay, so what exactly did he saw for hydrogen was he saw these different wavelengths of light being given off by hydrogen. So these were different wavelengths of light, 486 nanometers, 434, 410, 656. Those are different colors in the visible spectrum of light that were given off when these electrons change spaces. So what that means, he came up with this kind of energy diagram that showed the different distances that electrons could travel from the ground state, energy level 1, to more excited states, all right, up to energy level 5. Okay, electrons travel from this ground state to a higher energy level and then back down again. That gave a different wavelength of light off. All right, so Bohr kind of tried to explain this by electrons traveling different distances, and that gave off a specific wavelength of light for every time a hydrogen atom was excited. All right, so how he did this, he came up with an equation. We call this the Rydberg equation, but we'll kind of look at that when we go through some definitions. But the first thing we look at is have a few definitions here. Okay, so ground state is basically the resting state of an atom. All right, so it is the lowest possible energy state. Okay, an excited state is when an electron absorbs energy, it moves to a higher energy level, and it is unstable. So it doesn't really like the excited state. It wants to move back down to the ground state. And when that happens, when electrons move back to ground, oh, I'm messing that all up there, ground state, they give off energy. I could write here. I'm getting kind of, you have to bear with me here. I'm down at the bottom of my trackpad here. They give off energy in the form of visible light. All right, so you have a ground state, it goes excited, goes back down to the ground state, you give off an emission spectra. Okay, so that emission spectra is a quantized amount. So what I mean by a quantized amount, that means it's a specific packet of energy, basically a discrete unit. So a quanta is a unit or packet of energy, basically. All right, so